Now I am going to make one proposition over here. So one important thing I forgot to tell you is that the eigenvector is always non-zero. So most of the students commit mistake whenever we talk about eigenvectors. Then they say that they actually uh, get eigenvector to be zero while solving the example. So keep that in mind. Your eigenvector is always non-zero, and never say the eigenvector. Always say a eigenvector or an eigenvector, because the reason is this. Okay. So whenever we are having a linear map, obviously V is a finite dimensional vector space, and V is an eigenvector of t corresponding to eigenvalue alpha. So it means this is satisfied, that is t of V is equal to alpha V. Then the multiple of V, the scalar multiple of V, that is BV, is also an eigenvector of t corresponding to eigenvalue alpha. That is why in the last example, whenever we took multiple of 1 0, we got that to be an eigenvector, and the eigenvalue is same. See, always we get 2. So that is what I am saying. So whenever V is an eigenvector corresponding to eigenvalue alpha, then the scalar multiple, that is BV, is also an eigenvector corresponding to eigenvalue alpha only, right? So the proof is simple. We have to prove this, right? So I will start with LHS, and I can easily show that this is equal to RHS. I will call it as some star. So I'll say consider LHS, that is nothing but T of beta V. But since T is a linear transformation, it will be beta times T of V, since T is linear, which is equal to beta, but T of V is nothing but alpha V. Okay, that is from start. And by doing simple adjustment, it can be written as alpha times beta V, and that is nothing but our RHS, right? And that is what we wanted to prove. So therefore I said always say an eigenvector, right? See, an eigenvector, never say the eigenvector. So the MSc students also make this mistake, so keep it in mind. Yes, now let us see this example. If V is a finite dimensional vector space and T from V to V is a linear map, and if lambda is the eigenvalue of T, then this set is actually a non-zero subspace of V, and it has a special name. It is called as eigenspace of eigenvalue lambda. So why it is called as eigenspace? Because see the set properly. It is a collection of all those vectors V such that T of V is equal to lambda V. So if you look towards it, you will definitely recall the definition of eigenvalue and eigenvector. So basically this E of lambda is a collection of all eigenvectors corresponding to eigenvalue lambda. As we have seen, whenever you think of eigenvector, if you take any multiple of that, that is also an eigenvector corresponding to that eigenvalue lambda. So we combine all the eigenvectors, put it in one set, and we are calling it as what? Eigenspace. Now this example is for homework, so just show that it is a subspace of V, because we have seen many examples of subspaces till now. Only I would like to make clear this thing, why it is a non-zero subspace. Because your subspace may be zero also, zero in the sense it may have only one vector, that is a zero vector. So over here it is guaranteed that it is going to be a non-zero subspace. Non-zero subspace means it will have a non-zero vector, and the answer to that question is since lambda is an eigenvalue, you know the eigenvector is always non-zero, right? Obviously V is equal to 0 is going to satisfy this condition. It is very trivial. If you put V is equal to 0, your T of 0 will be what? 0, since it is a linear transformation, and lambda multiplied by 0 will be again 0, right? So obviously 0 always satisfies this property. Therefore we are not interested in zero vector, right? It is very trivial. We are interested in non-zero vector, isn't it? Therefore this set is going to be a non-zero, because as I have told you, your eigenvector is always non-zero. Since alpha is an eigenvalue, therefore you will be able to find a non-zero vector v such that t of v will be equal to lambda v. So that non-zero vector will be present in this set, and all multiples of that vector will be also present in this set. Obviously 0 will be there, right? And therefore it is nothing but what? A non-zero subspace, because this lambda is an eigenvalue. Okay, now since this is a subspace, we can talk about what? The dimension of it, because subspace means what? A vector space only. So later on in this unit number 2, we are going to talk about the dimension of this eigenspace. So that's all for today. So try to understand this concept well. You can see the video twice. You can go back and see again. So we will stop here. Have a good day.